Okay, so the uncertainty in the position of the the photons going through the lens arriving at A in the x direction, so delta x is half a wavelength. And so basically what this says is that we cannot actually determine the position of the focus, or the focus has a size, a spatial dimension of something like half a wavelength. And this is actually this is called the diffraction limit. This is a well-known effect in optics, and it basically limits the spatial resolution that a lens-based optical system can achieve, meaning that this lambda over 2, so whatever color of light you're using has a particular wavelength. You can't use a lens-based system to resolve structures which are finer than about half the wavelength. What happens if you have structures that are smaller than about half the wavelength? Well, those structures will basically be fuzzed out to a size of about half the wavelength. So they get blurred out. So imagine you have two point sources, two molecules, which are less than half a wavelength apart. Basically, they'd be fuzzed out to the point where they would look like there was just one molecule with a size of about half a wavelength. Now, implicit in this argument is that in fact this whole thing works in reverse. That if I have an object which is much smaller than the wavelength, that I can't use this lens. Basically what we've talked about so far is we're using this lens to focus light to a point. But what it also means is that you can't actually, if you have an object which is much smaller than the half a wavelength, you can't if you have two objects and that are each smaller than half a wavelength, and they're small and they're close together, you can't actually resolve them. Okay, let's look at another example now. Let's look at a classic case situation of a particle in a box, a particle in a one-dimensional box. So what we imagine here is that we have a particle that's constrained to move along one direction, on one dimension. So let's imagine that we have a bead with a little hole in it, so a sphere with a little, with a cylindrical hole drilled through it that's constrained to move, say, on a string, a frictionless string. And then let's imagine that we put two walls, and so the bead actually is constrained to stay between the two walls. Okay, so it's confined within the two walls, and the separation between the walls will just give a generic dimension A. So if we set up the problem this way, so that we know that that the particle is in the box, that is, it's confined between these two walls, then we know that its position. We know its position to precision of A. So we know delta x is equal to A. That is, we know that we don't know the position any better than A, and we know that it can't be any more than A because we know that it's somewhere in this box. Okay. Now, let's think about the uncertainty in the momentum. Now the particle, as it's sitting in this box, it might be moving around, it might be bouncing around in the box, and it might have an average momentum p with this symbol means average. Okay, so it has some average momentum p. Okay. And at any given time, its momentum p without the brackets, it can also have some instantaneous momentum, and so the uncertainty squared of the momentum of this particle is equal to its instantaneous momentum minus the average momentum squared. Now, the average momentum does not necessarily have to be zero in general for a given problem. Right, because a particle could be, whole box could be moving, for example, in one direction.